Okay. Okay, so what I wanted to explain in this last hour is something about duality. And so I wanted to understand something about this theory of automorphic forms and describe it in this dual way, this Langlands dual way. And I want to approach that in, kind of the ideas. I'm trying to push the TQFT point of view. So I wanted, how would TQFT tell you about discovering this duality, right? So I wanted somewhat an asymmetric point of view. I'm starting from the theory of automorphic forms and say, how can you describe it? And this is basically just a version of spectral decomposition for Hecke algebras. So what I want to say is that in a TQFT, we get lots of commuting operators. So we have a big families of commuting operators that we were describing from defects of various dimensions. And maybe when I say commuting, I'll be a little, we'll get into this more precisely later. It's maybe almost commuting. It's these kind of EN structures. So they're commuting with some, but the higher dimensions you're in, kind of the more commutative it looks. And so when you have a commutative algebra, of course, what you should do is take its spectrum. And when you have a module, so we have these spaces of states, so these are our spaces of states on various manifolds. They're acted on by observables. We're constructing particular observables from these defects, and we get these big commutative rings of observables, so we should take their spectrum and think of this as a module for that, and kind of spectrally decompose. So we should we take the spectrum and kind of spectrally decompose, or if you'd like, sheafify over this spectrum. Now, the physics and implementation of this is what's known as the theory of moduli spaces of vacua. It's going to be a kind of maybe non-traditional take on moduli space of vacua, the way I learned them from talking to Andy Knightsky. But this is kind of the slogan. Given a topological quantum field theory, we can always construct some kind of spaces out of it, kind of varieties. In fact, we're doing algebraic geometry because I'm doing specs. If there was nothing algebraic geometry necessarily here, I'm going to take some kind of spectrum and then think of sheafifying over that. And I hope to get a description of my original theory in terms of algebraic geometry of these spectra. That's the way I might start from my abstract TFT and try to describe it in terms of algebraic geometry. So we hope to kind of invent this dual side from the automorphic side.
So this spectrally, which category of form?
Yes. So I'll explain, and they'll have several different levels, right? I mean, the main answer is the Tanakian version. So mostly I'm going to think about tensor categories, kind of Tanakian reconstruction from them. But yeah, this happens in several levels because we said in TQFT we have these local operators. In any TQFT we have these. Again, I'm fixing my dimension. We have these local operators which formed an E4 algebra, and we have these line operators that formed an E3 category, and then we can keep going. You can have surface defects, and we can have domain Walters, but I'm really going to I'm just going to talk about these two levels. And these things are pretty commutative. Kind of on the classical level, both of these look like commutative algebras. And so I'm going to try to think about taking the spectrum of these and thinking of sheafifying or decomposing my theory over these spectrum. And the spectrum is some version of what could be called the Coulomb branch or moduli space of vacuum.
You don't have to spend time answering this, just in case you can say something. Sure. So when you say things like these operators acting on states in TQFT, when you're over this arithmetic situation, various analogs of manifolds literally exist because of a finitely algebraic closure power series. So these are literally because of arithmetic manifolds. But things like these cylinders and spheres cut out, they don't really exist.
They don't really exist.
So
but
how do you use this? What is your way of?
Because so for me, there are people who are trying to make sense of this rigorously of trying to define, but that's not my, for me, I use this TQFT as kind of a way of organizing structures that we do know exist. So the point is that the structures I'm talking about, they exist, and they're well known in number theory. And those are the things I'm going to use. I'm just going to use the TQFT way of thinking about them.
So somehow their behavior is suggested by the pictures that you can actually
Exactly.
draw.
It matches it kind of shockingly well. The things we already know are there in the theory match shockingly well what you would expect. So I really believe it exists, but I don't, it's not.
Why do you say they don't believe the pictures don't exist?
I'm saying I don't know when I draw a picture like this, I don't know exactly where this object lives, right? I mean, when I say arithmetic,
Ben-Zvi was code for a speck of a global.
yeah, so that exists, but it's in no sense a three manifold.
Was that wrong?
No, that's right, but it's in no sense a three manifold, no traditional sense of three manifold, and crossing it with an interval. Now where am I living? What category? And then removing a point.
On an analogy to.
Yeah, yes, exactly.
There's no
Yeah, so Mignon is pointing out that this picture where this is speck of a ring of integers of a number field cross an interval minus, so Peter Schultz wrote me some email where he sort of seems, I think he probably knows how to make sense of this.
Really? I say.
Well, at least at this point, he definitely had some. So they will exist, but
There's no
the future is now, but yeah. Okay, but anyway, I'm not going to use it. I'm just using this as a metaphor, but okay. So what I'd like to do is take these things. You can try to do the same thing with lower dimensional operators that get more and more complicated. We won't need them. I'm just going to talk about these two levels. The first level is not super exciting. It's good to point out. So let me point it out. We said, what is this local operators in this? Local operators in my theory was the cohomology of the classifying space of the group, which is a commutative ring. And so I take it, so it's really commutative. It's not just E4. And when I take spec of this, I get functions on something. Before I wrote it as Cartan mod value, let me not write Cartan, let me write dual Cartan dual. And there's a kind of a annoying thing maybe, or wonderful thing, depending on your point of view, which is a shear.
So V and star both mean algebraic dual.
They both mean algebraic dual, but one of them I think of as a Langlands dual, and one of them is a linear dual. So this is the coadjoint representation of the dual torus. That's going to be important to the why I want to write it that way for a reason. Or maybe if you'd like, you could think about it as coadjoint representation of the dually algebra up to some grading shift, and then kind of geometric invariant quotient. But what I want to write it in terms of the dually algebra. So this is the what physicists would call the Coulomb branch. These are the Coulomb branch operators for this n equals 4 Yang-Mills at this twist. Okay, this is not a super rich space. Algebraic geometry of this vector space is certainly not going to recover for you the whole theory of automorphic forms. So just thinking about this space, clearly not enough information. Where things get going is this category of line operators. And in the line operators, so what are the line operators? Well, now let me be a little more careful than I was before. Inside of the line operators.
David, just,
Yes.
I just forget this, but there's not, this E4 thing is actually commutative.
It's actually commutative. Yeah. Yeah. So it's
Even
really,
in the arithmetic stuff, there's nothing.
yeah, there's nothing cool. Sadly, I mean, it would, yeah, it's just commutative here. Okay. There's a closely related paper of Brian Williams and co-authors where non-commutative for algebras appear in closely related contexts, but yeah. Inside of this, there's an abelian category. So I've been kind of very sloppy about derived versus abelian. There's something, let me call it, inside of there, there's the familiar category of line or Hopf operators, which is identified. This is the content of the geometric Satake correspondence with representations of the Langlands dual group. So this is kind of the start of Langlands duality from this point of view. You pick a collection of line operators that you understand, and you can describe them as a tensor category. This is a tensor category. It's a symmetric monoidal category. This guy is also symmetric monoidal. This is an equivalent. And this is, if you'd like, this is the definition of the Langlands dual group. by Tanakian reconstruction, this tells you what this group is. So that's what I'm going to take as. So now I've defined the dual group for you. Okay. I don't know, the SL2 goes to PGL2 and things like that. PGL2 and SO odd goes to symplectic groups and stuff like that. So but people have probably seen these tables many times, so let me know. So that's where the Langlands dual group comes from. And so that's kind of the fundamental. So what we're going to do is we're going to use this to try to say, what does that tell me about the theory? So I have this again, so I have this line operators, the friendly line operators, if you like. And the friendly line operators are representations of the dual group, which I'm going to write in a fancy way as sheaves on the classifying space of the dual group. That's just another way of writing this thing. And what this means is that, so I have now a kind of approximation. So what does this mean that this, so the kind of the spectrum, so this is what I mean by spectrum, the Roman's question. Here is spectrum, here this is a tensor category, it's Tanakian spectrum in the Tanakian sense, maybe I should put a quotation mark, but it's a version of spectrum of this tensor category is just points mod the dual group. So that's basically just this statement reinterpreted. Now, so this is another approximation to my moduli space of Becker, to my spectrum of my QFT. I think this category of line operators, take it, think of it as some commutative ring, categorified commutative ring, and it's a ring of functions on what? This space. So that's my next approximation. And now there's a tension here between the two statements I made. They don't fit together yet. I'll fit them together in a second. So just to preempt that. It's not quite clear how this guy relates to what I wrote yet. But I'll answer that later. But for now, once we identified this, we now have a big commutative algebra of operators, and the Langlands program says, let's decompose everything under these operators. The operators give me these representations of the dual group. They act on everything in this theory. So the entire AG theory is linear over this space. So it kind of follows just formally from this TFT structure, at least in the kind of the Betty context. What you get is that this theory AG kind of sheafifies or localizes over this classifying space. So what do I really mean by that? So this is a kind of a slogan. And let me make more sense of this. This slogan is what's known as the spectral action in the theory of automorphic forms. So, for example, let's suppose we're in the context of geometric Langlands. So we have a curve over an algebraically closed field. So we have this category attached to this curve of an algebraically closed field. At every point, I can think of putting one of these line operators. So I get this action of this tensor category. So this is the category rep G check. Rep G check acts on this category for every point. Does this picture make sense what I'm drawing?
No.
No.
Those are line defects.
If the line defect, there's another
dimension we have the plot.
Yeah.
Okay. Yeah.
And so this category is a module for rep G check, but it's a module at every point. And this is where Brian's talk comes in extremely usefully for me, because it exactly tells you how to assemble all of these together. Because really, rather than a point, maybe I could think there's a little disk here. There's an action for every disk. If I have another disk nearby, I also can think of putting that defect there. And if those two disks sit inside of a bigger disk, then we get this multiplication on rep G check, which is exactly our tensor structure. So it actually follows formally from this. What you get out of this, and here I'm being a little, I have to be careful if I'm in what version of topological quantum field theory I'm in. If I'm really in the honest QFT, the kind of Betty setting, this follows pretty formally, otherwise I have to think harder. But what this tells me is really that the factorization homology over sigma bar of rep G check acts on AG of sigma bar. This statement, this is just a fancy way of saying I have an action at every point, and they satisfy the tensor product relations. This is exactly how Brian defined factorization homology, right? For every disk or every point here, I have an action, and they glue together under the embeddings of disks.
Sorry, what are you, what, this is, so this rep-G check is now a factorization algebra.
It's a, yeah, it's an E3 algebra. Here I'm only using, yeah, it's an E3, well, here maybe I'm using E2, but it's actually symmetric monoidal, actually computing. So, it's overkill.
Right.
But, so this has a different notation. People also write this as a tensor product. It's kind of copies of, it's some kind of version. This is very similar to some adelic version. You have an action of rep-G check at every single point. So really there's an action over tensor over all points of sigma of rep-G check acts, but this factors through some quotient. That quotient is this factorization homology. And that's the thing that which naturally acts. So that's what you get out of looking at line operators. And this thing is not
But
actually.
is this somehow the definition of this integral with respect to sigma bar?
Yeah, that's how Brian defined it. It's a co-
So
Yeah, he defined it as a colimit,
okay,
and that just means it's quotient
I see.
in this case. So I just have a bunch of actions at every single point, and they satisfy some natural coherences. The point is that this thing, this looks scary, but it actually has a very simple answer. It's just sheaves on the space of flat G-check connections on my surface. G-check local systems. That's what this thing is. You can just calculate it. So space of flat G-check connections on sigma, that's exactly what this is. So it just, you have a G-check local system. So let me write that again. What do I mean by AG sheapifies over sigma? If I look at the theory on my manifold sigma bar, I can look at the space of maps from sigma bar to point mod G check. Now here, sigma bar is kind of a, I'm thinking of topology, this algebraic geometry. So here I mean really, if you like, locally constant maps. I'm not thinking of sigma bar as an object of algebraic geometry, object of topology. And this is the space of local systems of sigma. So this is what's called the space of Langlands parameters in this context. So it's just the space of local systems of sigma. So
Sorry, what was that? Langlands parameter?
this is called Langlands parameters. Here, Langlands parameters for me just means these local systems. So if I'm in a topological setting, I think of these as representations of the fundamental group into, this is, in a Betty setting, honest manifold setting, this is representation of the fundamental group of sigma into G check. It's a character related.
Sorry, before I forget that computation that
Yeah.
you get quasi-coherent, quasi-polar factorization homology. Is it in your paper?
It appears in a paper I wrote with Nadler and Francis. I think it's kind of an exercise. I don't think that's, we say it this way, but I think it's it's an exercise.
Yeah, well, it's an exercise for you, but.
Well, it wasn't for us at the time, but I think now like any first year grad student in topology. Just yeah.
What's the version of this when you're over sigma, over like a curve over finite curve?
Right. So let me not answer that carefully. So the claim is that I want to claim that it follows from TQFT formalism that. Let me pause on that for a second. I'll say something about that. In the Betty setting, this is kind of a tautology. I mean, very close to tautology. In the Durham setting, there's I'm not going to explain all these, but there are different settings for geometric lengths. In the Durham setting, geometric length, that's where we study D modules. This is a hard theorem of Gates-Gray, the vanishing theorem. Vanishing theorem basically says exactly this statement, that the action of all these Heck operators factors through sheaves on the space of local systems. In the setting of these Fontaine curves, in the case of the setting of the local fields, this is a theorem of Farley and Schulze. This is the special action theorem. Again, it says that you look at this category associated to your local field, it's acted on by some space of quasi-coherent sheaves on a suitable version of Langlands parameters. And this, by the way, is one good reason you might want this big category rather than inside of here, there's the more concrete looking category representations of the p-adic group. That's not preserved by these Heck factors. This is the better object, partly because it has the right spectral action. This is kind of the main theorem in some sense of Farley and Schulze.
Okay, so this AG sigma part, this is in full or something like that?
No int codes yet. So AG, this is just this is sheaves on Ben-Zvi on the point content.
No, yeah, AG sigma part.
This is sheaves on Ben-Zvi, Ben-Zvi on sigma bar.
What kind of shape?
Dependent in either D modules or constructed. There's an Ital, a Durab, and a Betty version of these sheets, but we're not.
Oh, I see, okay.
But the topological sheets, we're not in the. Yeah.
I see, and the fuzzy clear and then they're acting.
Yeah, exactly. So this is the basic step that tells you this is not the geometric Langlands or Langlands corresponds yet.
Yeah.
We're not saying an equivalence of two things, but this is called the the automorphic to Galois direction. This is saying that the automorphic side naturally lives over a space of Langlands parameter. And I'm claiming it's something kind of very, again, these are hard theorems, but you could they fit perfectly. You could predict them from the TQFT. They kind of, if you like, maybe the other way around. They kind of support this TQFT idea. Okay, so what to Charlie's question? So what I don't want to get into very carefully. This is in some sense behind the work of Vincent Laporte in the function field setting. In the function field setting, if you just naively look at the head algebra action, it's not enough. You need more operators. The naive action of these loop operators that you just get is not enough to really give the kind of decomposition you want. He introduces bigger thing called excursion algebra. But basically what I want to claim is the same principle. What it's actually saying is the same principle. So I want to claim that this is in the TFT setting. This is I want to claim a formal property. I don't know if it's documented carefully anywhere, but the value of the TFT on anything, including on a three manifold, will sheafifies lives over this space of Langlands parameters, the space of local systems. So it's this guy's not affine in general, so but that's why you have to be more careful. But it's function in particular, it looks like a model for functions on this. So it looks like so it's a module over functions on the character variety. So that's a feature. So that's, if you like, what you get in the Langlands correspondence space of automorphic forms are modules over commutative rings, and those commutative rings have natural interpretations as functions on representation spaces of Galois groups. And that's just a statement that the whole theory, so I guess what I want to say that this, from a mathematical point of view, this value on a sphere is some kind of center of this TQFT. It's some version of a center, it could be an precise, and this is some fancy version of saying any algebra is a module over its center. Or any algebra is an algebra over its center. So any algebra sheafifies over spec of the center. That's the kind of the one-dimensional version of these statements. Okay, so this is, I claim, pretty formal, at least to predict. Again, there's a lot of deep math in making these into theorems, but these are the spectral action, but this is natural, very natural. So I'm saying you can guess a lot of the Langlands correspondence just once you know these line operators. And you get excited and you make a prediction, and you might make this kind of prediction that the theory of automorphic forms is what you just get by looking at this picture. Let me call this V-check naive, just to point out this won't be correct. And this is exactly what Brian said is in the first talk is that there's kind of an obviously wrong guess you can make. And the obviously wrong guess you can make is what if you only knew this structure, you could just make the following kind of guess is that, maybe AG of a three manifold should be something like functions on the corresponding character variety. Or maybe AG of a surface should just be just the thing that's acting. And so we have a commutative algebra acting at every level. And these guys fit into, I guess I should say, these guys fit into a TQFT. This is what I'm calling BG check naive. This is some version of this DF theory. It's just, and what is that version? Is to every input, every manifold I put in, I look at the space of maps from this input into point mod B check, which is just, this is what the space of local systems is. So that's, if you like, some kind of sigma model, some simple gauge theory. And I could just linearize it. This is an algebraic object, look at algebraic functions if I'm trying to get a vector space, look at sheaves if I'm trying to get a category, and so on. So there's something naive you can write down just from this data.
So you're saying that twisted n equals 4 is not really a BF theory?
Let me. This is wrong. I don't know my BF theories well enough to. I think if this is what the BF theory, if this is exactly the BF theory, then I think we have to be careful what exactly we mean. So let me not. This is wrong. And in fact, it should have been. You're right. So the naive guess is what what am I saying here? I'm saying this theory is a model over some algebra, commutative algebra, and this would be saying that the module is free of rank 1. Saying that that module is isomorphic to the algebra that's acting. That's what these kind of cases say. So that's the kind of the naive version of the Langlands correspondence, is that this algebra is just a module free of rank 1. This is not, it's not terribly far from the truth. It's a good starting point, but it's not quite right. And one of the ways in which it's wrong is the theory of orthoparameters, and that kind of pops out very naturally if you just think about this TQFT picture a little more carefully. So this is somehow the wrong slogan. We did get, so yeah, so let me make a better slogan. So we got a slogan, we found some commutative algebra of operators and we sheafified everything over it, and we said, okay, that's a pretty, maybe it's just the structure sheaf. So a better slogan, you can ask is, let me have a slogan that would be repeated, since its states are given by some kind of geometric quantization of some space, and they're acted on by observables, which are some kind of deformation quantization, and the idea is that one acts on the other. But what we took here, what I've given you access to is observables. I haven't yet given you the states. What I've looked at is all these rings of operators, but deformation quantization does not recover geometric quantization in an obvious way. You have to get a constructive module, a small module, right? You have to take some kind of square root in some sense. This is a geometric quantization, it's kind of art, deformation quantization, so it's a nice science. And so we've kind of solved this part of the problem, we haven't solved this part. So let me say it this way. If I take this, I guess I didn't use this notation. It's kind of moduli space of vacua of the topological quantum field theory. So here Z is my QFT. Let's say it's a 4-dimensional QFT. So my moduli space of vacua, I just mean spec, maybe in this Tanakian sense, of the observables. So that's the kind of thing we've been looking at. The point is that this ring of observables is not really commutative. It was
E4?
Yeah. And that non-commutativity means that this speck of observables, well, what this really looks like is it looks like reshifted symplectic space. 3 being 4 minus 1. So in other dimensions you get, yeah.
This observable is like Z of S3.
Well, right, okay, so what I mean by this, I'm going to have, really I have several different approximations. I could take Z, what I really would like to do is Z of S2, which is my tensor category, and Tanakian spec of this. So if you'd like, you could take spec in the Tanakian sense of Z of S2, or you could take spec in just the usual sense of Z of S3. And these are not the same, but this is optimization. And you would get something better if you looked at more and more defects. So this is some approximation. This is the most coarsest approximation to my moduli space of vacua. This is something smarter. In theory, I would get even smarter things by looking at higher defects. So this is kind of the sweet spot in the geometric Langlands, but this guy wasn't so interesting. But yeah, that's what I mean. And the point is that this is really looks something like something that's shifted symplectic. Really, we're getting the quantization of that. And what we need to do is deformation quantize it. What?
You mean geometric?
We need to geometric quantize it. So what we have is a deformation quantization of the space. That's what we get out of observables, essentially by definition. And what we need to do is geometric quantization. So a slightly more precise way to say it, the integral over M of the observables is going to be some kind of deformation quantization of this space of maps, these locally constant maps from M into this space. And what we need to do is geometric quantization of this. What I really want is the value of the theory on M. This is a modulo over, this is going to be the geometric quantization. So let me try to spell out what this means more. So this is kind of slogans. I want to say a little bit more what this means in geometric Langlands in general, and then how that applies to periods. So that's how we're going to try to discover periods. Okay, so yeah.
This might be more of a question for physicists in the audience.
Huh?
Is this supposed to be close to the low energy limit of the gauge theory? Or-
Yeah, so I mean, here, if you like, this is the kind of like the Coulomb branch of the physicist might write it, and this is remembering the residual gauge symmetry on the Coulomb branch. So I'm remembering that this is that on the Coulomb branch I still have.
Residual abelian gauge symmetry?
Not necessarily, right? I mean, so like generically, I say
Points on the Coulomb branch, of course, you have unbroken, not abelian.
exactly. So this remembers all of those, right? So generically it might be abelian, but this is remembering all the. So this is a better approximation. I don't think I should think about these in energy scales, but this is a kind of a better approximation of the theory, which I remember not just local operators, but line operators. Yeah. Now, so, okay, so how does this have to do with geometric? So these are some slogans. How does this have to do with anything? And the main point is that, you know, as I tried to hint before, local operators in this theory are not actually just representation of the dual group. So, so I said this contains representations of the dual group or sheaves on point margin check. But it's something bigger, and there's a theorem of Bezokavnikov and Finkelberg, which says what this actually is. And what this is the derived geometric Satake. Satake of Bezokavnikov and Finkelberg that says that this looks like sheaves on the coadjoint representation with some shift up to conjugation. Okay. So the difference between these is that now I have the whole coadjoint representation appearing, not just a point. The coadjoint representation is sitting in some non-zero cohomological degree, which is why I didn't feel it in the heart before. But it's a smarter. This is something smarter, and you kind of knew that something like this had to happen, right? In that before we had the Cartan shifted mod algorithm, we didn't see that in the naive geometric Satake. The local operators already told us there's something richer here. So if you want to combine local operators and line operators, you need to get something smarter. And that's the answer. Okay, so now what is this space? Let's give another formula.
Parallelogram, you have a V, a star.
Yes.
Parallel.
Yeah, so you know what two of
That's
those
a shift.
and then I need just clovers and yeah.
That's a shift.
That's a shift. It's cohomological shift. I mean, I think people traditionally would write this as shift by two. But
Oh, okay.
no, I like that shearing notation.
Oh, I see.
So
That's what you mean by shearing?
yeah, it's a shift. So what is this space? Another name for it is just the cotangent bundle of the classifying space with a shift. Maybe I should write the shift and go away. So the point is that this space that appears in Bezokavnikov Finkelberg, this space is itself a shifted cotangent bundle. In other words, this is a three-shifted symplectic space. So you already see some symplectic geometry right here. That when you try to understand line operators, they really look like a three-shifted symplectic space, or rather, this guy with its E3 category structure is kind of deformation quantization of this space. So it's slightly non-commutative. This category is slightly non-commutative, and that slightly non-commutativity is measured by the symplectic form on this space. Okay. So let me not make that precise, but it is a precise statement. Okay. So the point is that your local operators were slightly non-commutative, and that tells you that all the naive pictures I drew have to be amended, because I only use part of my line operators. This is the full collection of line operators. And when you amend things, you discover a richer version. So and now I'm going to be quoting mostly theorems that I learned from Dario Geraldo, right there somewhere. But there's now if you get this picture, if you integrate over a surface this full category of line operators, before we just got the space of local systems, now what you're going to get is roughly, let me write that, roughly it's sheaves on the shifted cotangent bundle of the space of local systems. So there's this extra cotangent bundle. Why is it 1? Before we had 3, and we integrated over 2 dimensions. We're mapping, so that just maps, this is just maps into that thrice shifted cotangent bundle. Really, when I say this is what I really get is I get the deformation quantization of this space. So this is a smarter version. This is Geraldo's theorem. It gives a slightly more precise understanding of what structure do we actually have. So what we actually get is that the space that has the surface is a module for the deformation quantization of this cotangent bundle. So it's something like a D module, like something a module of a differential operator, is just with an annoying shift, wonderful shift. And so, before we made the naive guess that it was just the easiest thing to do, just sheaves on the space itself, but there's nothing forcing that to be there. It could be something, this is a complicated singular space, and this is going to, in general, this is a more interesting module that has a micro-local aspect and knows more about this cotangent model. So that's the picture that this is, really I should mention, this is the interpretation of, if I go back to Rankin and Gates coordinates. This is the theory of scalar support, or their interpretation of orthoparameters in the geometric Langlands context. So you get a similar statement now on a 3-manifold, that if you look at automorphic forms on a curve over a finite field, you don't expect it to be functions on the space of local systems, but you expect it to be a module for some kind of version of differential operators. Quantization of now an unshifted cotangent bundle. And again, and the answer that's now expected is something like volume forms roughly on this space. They have a formulation of the Langlands conjecture of function fields, which is, it's not really functions, it's some version of volume forms that's something that knows something very subtle about the singularity. This is a very complicated singular space, very derived space. And this is a smarter thing, and you can't predict which exact version, but the idea that it should be geometric quantization of this follows from just the physics point of view.
So,
Yeah.
this thing on the left, I guess it's related to what we say in the paper. It's a book rotation equivariant, shapes, and I guess this corresponds to quantizing the just developing algebra.
It's not unrelated, but it's not exactly that, right? So your theorem is about the SO2 equivariant. So when you turn on the rotation equivariance, this deforms to differential operators. That's kind of a shadow of the fact that you have an E3 structure, right? Well, it's an SO2 equivariant E3 structure on this thing, and that E3 structure is non-commutative. That your theorem measures that non-commutativity. Here, I'm not using that SO2 equivariance exactly. Well, in some sense I am, because I'm putting it over a global Riemann surface. So I mean, it is very the same, there's close circle ideas, but the claim is that when you integrate that category over Riemann surface, you get this deformation quantization. It's what Dario calls H. But yeah, it's a measure of the non-commutativity of that. And yeah. But yeah, it's the same non-commutativity that you're referring to, but it's appearing in a slightly different form.
I guess maybe the curve is sigma bar is 2, it's 1.
Yeah.
Dependent.
Yeah, I think that's right. Yeah. Okay, so this extra microlocal correction, I don't have time for this, but this is basically where the theory of orthoparameters is. So that there is a refinement of the Langlands conjectures that takes into account extra data. There's some extra, in the physics, this is the existence, there's extra scalar fields in the theory that we notice exactly at the singularities. This is, and those extra fields are exactly what appear, for example, in the non-pole boundary condition. So there's some interesting extra fields in the theory, and that's where this kind of ortho corrections of Langlands come from. But let me not get into that anymore. What I'd like to do is apply this kind of philosophy to periods. Right? And I want to apply this to the theory of boundary conditions.
Wait, you said you were gonna do geometric quantization.
Yeah,
I
so
missed it. Where did you do geometric quantization?
I didn't do it. I said I needed to, right? So what I said is that the observables in the theory
Yeah,
look like some quantization of this cotangent bundle. And so the actual theory, AG of a surface, that's the category I'm interested in. It'll be a module for this. Before I made the most naive guess, which was just the most naive guess is just sheaves on the space of local systems. That's wrong. It's more singular, it's more micro-local. It has, you know, it has a wavefront set. The actual answer has some interesting wavefront set. The actual answer, now this is a theorem, Gates, Gray, and Raskin, and a bunch of people. The geometric Langlands correspondence over the complex numbers identifies this with some incoherent sheaves on this space of Langlands parameters. So maybe with nilpotent singular support. I mean, there's some adjective, so I don't have time to describe this adjective, but it's some version of this that has some wavefront set, has some extra singularities. It's still a module over this. It's a bigger one. So it's not just the free rank one module over the operators you had before. It's something more interesting. The difference between them is this Arthur parameters. Okay. So Gates, Gurry, and Raskin, and more people. Okay, so let me try to say something about periods to kind of finish. So I wanted to use this story to predict, you know, again, what's my goal? My goal is to predict what the theory of periods. So here I have a G variety X, and I have this boundary theory. For this automorphic A sub G, which on global, you know, includes the notion of X periods of automorphic forms and representations on local harmonic analysis on X, has different pieces in different settings. And now what I want to do is kind of predict what is the Langlands dual to this. How do you describe this on the B side? So I think this B theory, which is the naive theory but kind of corrected, this theory I get by geometrically quantizing these spaces of Langlands parameters. And I take that B theory, and so I don't know if that still counts as a BF theory, like this, you know, that's what I'm a little confused by, this theory that you had cotangent bundles of here. So there's I want to geometrically quantize these shifted cotangent bundle spaces of local systems. That's what the theory is doing. But so I think this B theory, it's supposed to have a boundary condition, which I'm going to call the L theory. We associate to some space M check. So like this is where M check I claim was going to be a Hamiltonian space with Langlands delivered. So what I want to explain is where does this M check come from? Where does this structure come from? So where do we make these conjectures? So again, we have this
LM check is the dual boundary condition.
exactly. So I have this kind of I don't know. Let me call it boundary condition as a member, and so I have this there's kind of a S duality exchanges boundary condition. So here a boundary condition given by a spherical variety, and we want to describe what the dual boundary condition. And what I claimed was this is the theory of L functions. This theory spits out L functions of Galois representations associated to something. So I want to say, where do you get that something, and how do you see something like L functions of Galois representations? Okay. So that this theory will spit out on a three manifold will spit out L values of Galois representations and identify them with periods of automorphic forms. So where do we get this from? And the basic point is, I claim that the basic starting point is this Poincaré formula. So what I'm going to extract from G acting on X, I'm going to extract. I drew a whole lot of pictures in my last talk, all kinds of pictures we can extract. They all have to do with harmonic analysis on. I look at X over some local field. Now let me just, let me take my local field, say to be a loop to positive characteristic local field. I might look at invariant functions. I might do harmonic analysis on this space And out of that, I want to extract some structure that will produce this for me. And what is that structure? So the picture I drew last time, one of the many pictures I drew was something like this. This picture appeared. It was a S2 cross an interval where I put a boundary condition on that end. What is this picture? So there's, I can construct an algebra we call the Poincaré algebra associated X. Poincaré algebra. So this is a version of what you might also call the relative Coulomb branch. The Coulomb branch for a boundary condition, for boundary theory. It's very close to the construction of Braverman, Finkelberg, and Nakajima of Coulomb branches. So we can start something we call, and it basically is that construction. So what is this Poincaré algebra? Well, first of all, what kind of a beast is it? It's, so what is this picture supposed to be? Let's just look at this picture. This guy, two-sphere, right? That was my E3 category of local operators, which is my Hecke category, my spherical Hecke category. What is this picture supposed to say? I'm going to get an E3 algebra object in this category. So these are the local operators sitting on a boundary. These are the line operators in the inside, right? So here's Brian's picture. Here's, so I have local operators on the boundary, and these are how they relate to line operators in the bulk. And this is line operators in the bulk. These are local operators on this boundary. So I want to, and this guy formally is going to be an E3 algebra in this category. So it's an E3 algebra in the spherical Hecke category. And what is it? It's not something very hard to say. It's just given by endomorphisms of this basic object. I have the constant sheaf on X of the local field on G of X of O. Take the constant sheaf. I think it's endomorphisms inside the Hecke. It's a formula, okay. What I wanted to, what I drew before, I claimed that when I cross this with a circle, I get this Poincaré formula for spherical functions. That's why I drew these vectors. This is in some sense a categorification of the Poincaré formula. This tells me instead of inner products of Hecke operators, it tells Homs between Hecke functors applied to this object. That's what this is doing. So it's some kind of categorical version of the Poincaré formula. And you get it just out of the TFT of X. Now what I want to do is I want to just interpret this line. Okay. So how do you interpret this line in the Langlands dual way? Well, Ben-Zvi and Finkelberg tell us how to think about the Hecke category dually, right? So this Hecke category is she's on this coadjoint representation, shifted, equivariant sheaves on the coadjoint representation. And now I'm telling you, so now think in this way, I tell you I have a commutative, or almost commutative, E3 algebra in this category. So now forget I said the words E3, just imagine I said commutative algebra. What does the commutative algebra in this mean? It just means an affine variety over this, something, an affine morphism over this guy. So I look at this space, G-check dual mod, let me ignore the shift for now. And how would I construct commutative algebra here? Well, I think it's spec. Just take spec of this guy. Well, relative spec, that's going to be some morphism, which is some affine morphism over this space. And this is the definition of M-check. It's just spec of this algebra internal to this. Okay? So we constructed out of just pure TFT an affine variety, something that's affine. So what this means, this is equivalent to just saying I have M-check, which is an affine variety, plus an action of this dual group. And now we get again things that explained in Brian's talk. If you think about the shifted symplectic geometry, this is actually not just something random, this is a Lagrangian. If you look at the same lecture of Pavel Safronov that Brian referred to, being a Hamiltonian G-space is equivalent to saying that this guy has some Lagrangian, it's actually a Lagrangian in the shifted sense. So this is a shifted cotangent bundle, and this is saying this Lagrangian. That's equivalent to saying that this is actually a Hamiltonian.
I think that's an inclusion.
No, so it's a Lagrange, so Lagrangian in this world are no longer subsets. This is what Brian was referring to, just like boundary theories are not boundary conditions.
Okay.
So there's a notion of Lagrangian morphism. This guy is some shifted cotangent bundle of the classifying space. I removed two just to, I don't know why. So this is shifted Lagrange, and this is a map, and the claim is that this is a beautiful observation, I think the theorem of Kalak, that a Hamiltonian G space is the same thing as a Lagrangian in this shifted symplectic manifold. I think that's really correct. So you could, so the point is, even if you don't think about Lagrange stuff, you obviously see an affine variety. The claim is that the TFT structure produces for you, it's not just some affine variety, it's actually a Hamiltonian G-dual space. And if you like, you see not just that Hamiltonian G-dual space, but you see its quantization. It's an E3 algebra. It's not just it comes with a quantization. And that's what you get. So the point is that this Coulomb branch, this is again a version of this BFN Coulomb branch construction. This is really just trying to describe the Coulomb branch. And you get but the point is that in this kind of relative version, you don't get just a symplectic variety, you get a Hamiltonian G-dual space.
Yeah, you got lost several places, but X was a spherical variety here.
Yeah.
In the eventual construction of M check, where does X? What is the input of X?
Well, I needed to give this algebra, right? This is spec.
Oh.
This is spec of this algebra.
Okay, that was that one.
Yeah.
That was the object.
And again, I kind of hand and hod. Really, I shouldn't think about this as being X. This should be about M, the cotangent bundle of X. So really, I shouldn't need to be polarized. There, you need some version of the theta, Weyl representation or something. You shouldn't need to start with something polarized. But it's easier to write down using polarization. This guy didn't come with a polarization. Sometimes it is. It's easier to understand what's going on when this guy is polarized. But really, the duality is between Hamiltonian G spaces and Hamiltonian G dual spaces. So in our paper, there's a precise conjecture. There's precise formula conjectured for this M check. We care how to build it out of the theory of spherical varieties.
Right, but it seems like in the spherical case, you just have a recipe for M check.
Yeah, that's what I mean. There's a precise recipe, and there's by the conjecture that it actually satisfies all the things I'm claiming it does. You can build a space called M check, and the claim is it matches this Plancherel construction. But more than what I want to claim is that it gives all the entire field theory, boundary field theory it gives matches the entire field theory I get from my period. So that's the. When did I have no idea what times are.
It was approximately 3:30.
It was approximately okay.
3:30.
Okay, so let me just finish by saying something. So this is kind of a construction at the heart of what we do. This is where Hamiltonian spaces appear. And really, again, this Hamiltonian space is really appearing. It's more of its deformation quantization. That's what we're building. That's this algebra. It's really some kind of deformation quantization. And so now you can try to build out of this the entire. So then you can make a prediction that the entire field theory that you get, the entire boundary theory associated to X, is dual to something you build out of this L. So I can tell you. Let me say a couple of examples of what kind of things this theory does. Well, since we don't have much time, let me just get to the punchline, which is L values, right? So let me assume for, to make life easier, is that my M check is polarized. So things are much easier when it's polarized. And let me make my life even easier. Let me assume it's a cotangent bundle of a vector space. Okay. This actually ends up being, well, okay, maybe not the cotangent. The linear case is the most important case, where I mean, it's a vector space. The polarized is not necessary. But yeah, so I'm going to assume. So what is this V? This V is now a representation of G check. Okay. So I'm assuming that my Hamiltonian space is linear. There's nothing saying it's linear in general, and there's nothing saying it's polarized in general. But let me specialize to that case. And so what I want to claim is that what this L theory attaches to a curve over a finite field, is, what is this? This is going to be, well, where does this live?
So wait,
Yeah.
L sub M check is a three-dimensional theory?
L of M check is a boundary theory.
The boundary.
L of
theory-
M check is a boundary theory.
Boundary theory in this four-dimensional.
Yeah, it's a boundary theory for this four-dimensional theory. This n equals 4 cycles infinity. And what I want to describe is what that boundary theory gives on various manifolds. So, the ones that we spend the most time on is what it does on the Riemann surface, on a curve, oh, sorry, I switched what I wanted to do. Where we spend the most time is in geometric Langlands, where we get an object in the category of sheaves on the space of Langlands parameters. So what we call the L sheaf. And what we get on a surface is, something like a function. Let me just be a little more honest. What we get here is it's a volume form. Let me ignore the difference between them on the space of local Langlands parameters on my curve. Let's ignore the difference between volume forms and functions. And so basically, what kind of beast is this? It's something like a function. So let me think of this as really being a function. It's something like a function on the space of Langlands parameters. So to each Galois representation, it's associating a number. And the claim that number, this is the L value, is given by take a Galois representation and associate to it the L value associated to this to rho and V.
Isn't L function a function of S?
Yeah, S is 0.
And S equals 0.
Yeah, should have been normalized. I'll get it. Yeah, so I'm ignoring S is not playing a role in my story. Let's look
It's like this, the center of the reciprocity.
Yeah, it's a critical L value. So I get a function on Langlands parameters, and that function is given by an L value, the L value associated to V. Now, now you might ask, how do you see that? What does that have anything to do? Let me just write down one formula. And that formula is, how you, and let me maybe give the formula, and because that formula is what you might just guess from thinking about boundary theories. Before, remember, I had this map. G bundles with a section of the associated X bundle. So I clicked on G, and period was giving in terms of push forward along this map. That's kind of a very natural, obvious thing to do from the physics point of view. I'm going to write down the exact same thing on the Langlands dual side. I have the space of Langlands parameters in local systems, and I'm going to look at a local system together with a section of the associated X check bundle. So here I'm assuming that M check is the cotangent bundle of the X check. Maybe in my case, this might have been a vector space. But I don't need it to be a vector space, but I do want it to be in a polarized setting. Suppose you're in this situation, then the claim is, so the analog of period, what it was a period was you take an automorphic form and you pull back and you integrate, or you can just take the function one and push forward. We're going to do the exact same thing. So with the L sheaf, L sub X check, this is when we have on the two manifold, this is just given by the push forward along this map of the dualizing sheaf. It's an object of this category. Or the L function, I'm going to write the same notation. If you like push forward the function, maybe let's call it devol, volume form, which is now a volume form on the space of local systems on sigma. This is, this is in the two manifold case, this is in the three manifold case. It's the same formula everywhere, right? And now the question is, what is this? And this is what I just wanted to end with. Say, this relation to L functions just comes from interpreting, to take the L function of a representation, the claim is that you can, the L value of this representation, you can identify that with the volume of the representation, and you take the fixed point set for your Galois, or maybe let's call pi 1, acting via, how do you write this? rho of phi one. So rho is going from your Galois group to the dual group, and now which is acting on this vector space. So you take your Galois group. So if you like, this is just a version of just say this is a version of just say Galois cohomology. Galois cohomology of V as a representation of Galois group. So that's this fixed point locus. Now looking at functions on this, I'm looking at the volume of this derived fixed point locus. So that's an interpretation of the formula for the L function, you know, this alternating product of characteristic polynomials of Frobenius. You can interpret it as being a volume. Here, this is a categorified version. This guy is sort of taking rho, now a geometric rho, to just differential forms on the fixed point set. That's a vector space you attach. So this L sheaf to each local system, you took the vector space of volume forms on the derived fixed point set. That's what this push forward means. And the point is that that categorifies the L function. When you take trace of Frobenius on that, you get the L value. So that's how you see L values appearing as the Langlands dual to the period. It's like the formula, the structure is exactly the same, but the nice thing about this is that now this extends, this has a version, a global, a 3-manifold version, a 2-manifold version, a local version, a global version, theta series, all that structure that we saw. Again, we don't prove any of this, but you can now make a whole family of conjectures that all the structures you see on the automorphic side should match exactly the corresponding structures you see here. So it's a big network of conjectures in all the settings. And I think I should stop there. Thanks.
Any more questions?
People, I mean, the people in geometric Langlands ever study actual 3 manifolds?
This is one of my favorite questions. And I mean, the people being like me and collaborators are trying to, but it's not one that, you know, it's on the Galois side, on the B side, there's some very obvious things to write down. You know what this B theory, I know what it is on the 3 manifold. It's just functions or maybe volume forms. If you know, look at volume forms on the character variety of your 3 manifold, everything derived. So that's a perfectly fine vector space. That's what this BF type theory, that's what this theory spits out on your 3 manifold. On the A side, I was very embarrassed for many years to ask this. I figured this must have been in page 2 of Kapus and Witten, and I somehow missed it. On the A side, we don't actually know. I think we, meaning the community, there isn't a really good understanding of what the vector space attached to a 3. You know, Kapus and Witten's theory will spit out something. It's not. There isn't a known good description of this.
Well, even when the 3 manifold is a 3-sphere, is there something?
Yeah, you can for 3-sphere you can calculate for simple 3 manifold. You know compatibilities of TFT. So for example, if it's a mapping torus, you can predict it because you know what you attach to a 2 manifold. You know, you can use a Hegardt splitting to give a prediction, but there isn't an intrinsic good description. In the Abelian case, everything is fine. Again, nothing's hard in the Abelian case. So David Jordan and Sam Gunningham and Pavel Safronov have been studying, maybe partly with me, the quantum geometric Langlands theory on 3 manifolds. And that has to do with Skane modules. So they proved some deep theorems about Skane modules of 3 manifolds. That's the vector space. And so for the quantum Langlands doesn't really tell the difference. The A side and B side kind of look the same. But it does make really interesting conjectures. The Skane module for G and G dual should match. And they prove these in some cases, and they're highly non-trivial Langlands dollars. So for the quantum theory, you know what these vector spaces are. And you know, again, Dave Jordan, Gunningham, and Safronov have been studying them. For this theory, it's kind of embarrassing because, you know, it feels like the basic question: what is the space of automorphic forms on the 3 manifold? I don't know of a great answer to that.
I guess this leads to my second question, because I mean, there are all the other twists that you can write down. So in the geometric setting, I mean, there are versions of your conjectures.
Yeah. So yeah, this is another really sad thing.
Sorry.
No. Wait, no. It's sad in a different way. The theory of boundary conditions. When I first learned about this, I thought it would be really cool. Let's just do the quantum group, you know, the Q version, the quantum version. And the sad thing is that there are essentially no boundary conditions, almost no boundary conditions for generic Q. has to do with kind of the non-degeneracy of the
QFT that they took by eyesight.
Yeah, so for generic Q, the theory is much more non-degenerate, has all the line operators disappear, there's a lot less structures. And the Eisenstein-Sears, where the porous boundary, that domain wall between parabolic induction always makes sense, but that's essentially the only thing. This has to do with co-ideal subalgebras of the quantum group. They're just not being that statement wrong. But for generic Q, most of the all the richness of periods only seems to exist. Well, maybe on roots of unity, but for generic Q, none of these richness survive. Very few. I should mention there's papers of Braverman and Trevkin and Finkelberg. There's some collection of these they call Gallardo conjectures. There's some example that's not literally true that nothing makes sense. But
yeah, I guess I was hoping that you could see M and M check as kind of being same, different limits of the same object.
Yeah, that's a sad state of fact. I mean, they're just not for generic Q. These things just don't exist. Yeah.
We interpret that as these boundary theories not having as much supersymmetry or breaking some supersymmetry with less.
I mean, they definitely. There have BPS boundary theories, but so they're as supersymmetric as they can be, but they're. Yeah, there's certainly nothing that from that to predict that they should exist for all psi. So probably then, maybe that's there's certainly nothing that predicts from the supersymmetry that they should exist for all psi, and unfortunately they just don't.
So do they understand the message correctly? The dual side can be constructed. Original side by kind of systematically taking spectra.
Let me say the slogan would be like the square of the dual side can be constructed, like squares of L values. So then there's an issue of taking a square root. So that's what the difference between, if you like, deformation quantization and geometric quantization. So there's a very nice paper of Venkatesh and Amina Abdurrahman about exactly this issue of square roots of L values. Symplectic L values has an interpretation of this kind. So I think that it's, if you like, the observables, what you get out of this formally is the observables and observables here that's a deformation quantization. They know something about cotangent bundle, but you have to extract the geometric quantization. Or in our paper, we have the statement on a closed surface. You can construct some natural Clifford algebras, and then that you want to find a module for. That's a similar version of this square root. You can write down some obvious Clifford algebras. This has to do, if you like, just think of what is Rosansky-Witten theory attached to a closed Riemann surface. I have a symplectic manifold. I'm supposed to get a vector space attached to a closed surface, and that vector space has to do with some kind of quantization of. So there's some vector space you can write down. It has some quadratic form on it. You can write down a Clifford algebra. But the vector space you're supposed to attach is supposed to be a spin module for that. So there's some square root. So it's the same issues that you always have in geometric quantization. So the thing you can formally write down is not the L sheaf itself, for example, but something like its square, like its endomorphisms. Or if you like, it's not the L value associated to V, it's an L value associated to V plus V dual, which is a kind of square. That's the thing that you get kind of formally. And then, so I'm trying to pitch that as saying, you get the deformation quantization, so to speak, for free, and then you have to, the actual thing you want is a geometric quantization.
How does this relate to special cycles? Space of shifts?
That's a fantastic question that I don't know of any. You mean like the work of Zhuoyun and Wei Zhang? Yeah. I would love to understand. There should be some interesting thing to say, and I don't have it. I don't know what it is. But that's a great question.
Could you give some examples of pairs of X?
Oh, yeah. So there's a whole table in our paper, and there's a bigger table on Jonathan Wang's webpage. There's a lot of examples. So yeah, I think the examples, let me say okay, there's one example that's sort of tautological. There's very few examples. The examples tend to be extremely non-obvious. There's one example that's fairly obvious, which has to do with, like, the identity self-domain wall of the theory. The identity self-domain wall has to correspond to the identity self-domain wall. you can interpret that as saying if you look at the group G as a G cross G space, you can think of G as a G cross G space, or if you like, T star G as a Hamiltonian G cross G space. That corresponds to the same thing for the dual group. This is the group because of the group period. This is just again some version of saying the identity is the identity. Again, I could think of this as a boundary condition for the G plus G theory, or as a domain law from the G theory to itself, and its identity. So that's the only example that I think is really obvious. Another example is, I'll probably get this a little wrong, but roughly speaking, let me write this and then I look at G mod U. This doesn't technically fit into the assumptions in our paper. Our paper always assumes affine spherical variety and the other annoying technical things. This is not affine. This is maximal unipotent subgroup, so it's like A2 minus the origin. So that's let me think of this as a G plus 4 space. And that guy is, so to speak, self-dual. And this is the statement that Eisenstein series has to do with, is an example of Langlands functoriality from the Eisenstein series realizes Langlands functoriality from the course. But it's like Eisenstein is dual to Eisenstein. So these are the examples that look kind of obvious. Let me write down the example that's highly non-obvious, very familiar to physicists, very familiar to number theorists, both in kind of exotic languages, right? The simplest thing you might have thought of is point. Right? That's a Hamiltonian G space. This is the Neumann boundary condition. So again, appeared in Brian's talk. This is the most obvious thing to write down is the Neumann boundary condition. Or if you like, this is the trivial period. Just integrate an automorphic form on the whole space. And the trivial period corresponds to the Whittaker period. So this is something highly non-trivial, which is like the non-pole boundary condition.
Oh.
So you take the cotangent bundle.
Oh, we know that.
Yeah. No, this is one of the cases we understand. I just want to say it's already, if you've never seen these things before, it's a weird answer, right? It makes you realize that everything is kind of, things are complicated. So the non-pole boundary condition, this is not the way I think a physicist would write down the non-pole boundary condition. It's a twisted cotangent bundle of G check mod U check. This corresponds in theory of periods. This is the picture I drew where you take a form and integrate it around this cycle, but against the character. That's the linear. That's called the Whittaker coefficient. What? I'm sorry. The constant. Yeah, it's a Hamilton. Sorry. I'm calling it this. I mean, P star of G. I take Hamiltonian reduction at a character of at a non-degenerate character of the uniform group. Yeah. So I'm thinking of it as this
Somehow that corresponds to the non-pole boundary.
Yeah, this is I can explain that later, but this is you can interpret this as a
What's the name?
non-pole. Actually, it was very embarrassing. I looked the word nom doesn't appear in this is one thing that we need to revise because it's most written. The first question is like, do you have access to it? And it's like, no, this is one of the most important examples in our paper, but that the physics words are missing. But yeah, the non-pole boundary, and there's more general non-pole boundary conditions associated to SL2 triples. We don't know what they all correspond to, but this is the principal non-pole.
You have to choose a residue for the Higgs field.
Yeah, this is the principal.
That's
the principal non-pole.
Principal.
The principal non-pole which is dual to the Neumann.
Okay, right.
This is the principal non-pole. There's a lot about these SL2, these nilpotent orbits play a big role in our paper, but we don't really know what all non-poles are dual to. Okay. So what are other examples? Now, one of the cool things in this theory is that it's symmetric, right? That we expect, well, this is it's all conjectures, that the duality is symmetric. If I switch the two sides, I get a new statement. So if I put P star side P mod U here, it should correspond to a point here. And in math, these are very different statements about automorphic forms. This is the Whittaker normalization of this is the statement about Whittaker normalization of modular forms, and this is a statement about the constant period. This is the kind of Tamagawa number. So they're very different mathematical statements, but they look the same. The one that I think is coolest sounding is let me write it in slogans. So there's the Gahn-Gross-Prasad period. So this is a really cool example of a spherical variety. And I'll mess it up. But I want let me do what is this? I'll get this wrong, but people in the audience will help me. Let me write it this way. You know, here I said a group is always a spherical variety for a group times a group. So I could have written this as a spherical variety for a group times itself. But the cool statement is it's still spherical when I make one side smaller. This is a version of saying that there's a multiplicity one restriction problem. And so you can look at any multiplicity one restriction problem gives an example. So this is a big subject in number theory. It's the Gahn-Gross-Prasad theory. And what appears
This is a split example. Like this is T star of that.
Yeah, he's started of this. Yeah. And the cool thing is that the dual side is non-split, is not polarized. So the dual side here, well, what is the group? I get, you know, SP2N times SO2N. And then this guy has an interesting symplectic representation, which is I take tensor, I don't know, what is that? What am I supposed to write? Let me just write V tensor W or something. I don't know. Take take a defining representation, tensor product and defining representation. This is a symplectic vector. One of these has an orthogonal inner product. One is a symplectic inner product. The tensor product has a symplectic inner product. This is a symplectic vector space with which is a symplectic representation of this group. Now, so the GGP story says that when you study periods in this setting, they're given in terms of these L values associated with this, or maybe square roots of L values associated with this. On the other hand, if you switch the direction, this is about what's known as the theta correspondence. The theta correspondence says that you can construct Langlands functoriality between orthogonal and symmetric. You can take automorphic forms. You can pass automorphic forms between orthogonal and symplectic groups. As
You
we
mean
realize,
theta lift? You mean by the theta lift?
theta lift, yeah. That theory of theta lift or theta corresponds. That's exactly what you get by switching these two, putting this on the automorphic side and this on the spectral side. This is now saying that you're realizing Langlands functoriality for SO2n maps to SO2n plus 1. So here we have just a map. This is just an annoying way of encoding just a map of dual groups. And so the neat thing here, I mean, we're not proving anything new about either GGP or theta, but the claim is that the two are actually two sides of the same coin. Depending which one you put on which side.
And do these have names in the physics literature, or do these have physical interpretations?
I think the answer,
I mean, if you hadn't told me, I wouldn't have recognized that was the non-pole.
right. So I remember when I think I was telling Akshay about Goyota-Witten for the first time, and he kind of went and he didn't. I think at the time he didn't understand. He's learned everything, but he was looking at flipping through Goyota-Witten, and I think he found this example there. And he got very excited. He basically found some version of this. I don't know exactly where it is. I can't understand Goyota-Witten, but he saw that the right formula. So that. So yeah, I think these some of these are studied. In general, the periods that we study are not typically the ones that are studied most in the physics literature. So it's hyperspherical ones are a different class, and we make some predictions of what their S dual is.
But they should correspond to boundary conditions.
But they definitely correspond to boundary conditions.
Boundary theories.
They basically correspond to boundary theories, and we're making predictions what their S dual is. And there's lots of examples. So these are the ones that can. There's probably a few more. There are a few more I can write down, but you could look at our paper.
Formal in some sense, or you can't tell.
Yeah, I think these all are. Yeah. Yeah, I didn't emphasize it's very important that all of these Hamiltonian spaces are also unbraided. They always come with a C star action.
Oh.
Yeah, all of our Hamiltonian spaces come with C star action rescaling the symplectic. So that kind of it's kind of some unbroken R symmetry.
Mm-hmm.
Thank David for that lecture. Thank you everyone for attending.